Good morning. Thanks for coming to this webinar. We are going to teach you how you can connect Spark and Cosmos with all the framework from FIWARE and where you can use machine learning with it. We are going to have a small introduction about all these things in order that you understand everything that is going on inside the FIWARE ecosystem. And later we will present a real example that you can also try. We will describe how you can download the example and deploy everything so you can have this up and running in your environment in a very simple way. So we suppose that you have some knowledge about FIWARE. FIWARE main component is the context broker, where you have all the information, and we will get all the information from this in order to do different things. First of all, we must show more or less what you can do with some of the artificial intelligence or machine learning or whatever you want to call it, to make some transformations over the things that you have there. You have the raw data, that is what usually you get, and you must process it in order to get some kind of information. This is usually done via some pre-processing. But to get knowledge of wisdom, you need to do other things. Usually, right now, the most trendy thing is to use machine learning algorithms. Machine learning algorithms are relatively easy to use once you know how they are working, and you can get very good results. But there are other ways of doing these kind of things. There is not the single way of doing all these things. One of the problems of all these kind of things is that we are really having a lot of information. For example, right now on internet, any social media site are producing a huge amount of data. We must take into account that today we are going to introduce things that are able to handle these kind of things. This is what is usually called big data, and are very different, the technologies and the things that we want to use when you are having, let's say, a small amount of data, that huge amount of data. Most of the things that probably you have been doing using R or using Python are very good to make different designs, but really, if you want to be able to digest all the kind of information that we have here, for example, all the events that Twitter is producing each second, you need a different kind of things. All these different kind of things are related to usually distributed systems where you have clusters where you can parallelize all the tasks that you are doing. Not all frameworks are able to do this, and today we will present a Spark that is really able to handle all these kind of things. First of all, if you don't have big data problem, perhaps it's not the most suitable for you, but also can be used in a more simple scenarios. But it's the only one that is used for all these kind of huge amounts of information. This trend is going bigger and bigger any day. As you have more communication capability with 5G and other technologies, we will get quite much more amount of information each day. This means that our clusters will need to be bigger, and we will need different techniques like the one that we will present here in order that you are able to analyze this. There are different definitions about what can be considered big data. Big data should be, in the rule of the thumb that you can use, is that if it does not fit in one single computer, you have big data. But big data usually comes in different aspects. One of them is the volume. As I have already shown you, most social media sites over internet are producing a huge amount of information, and a very high volume of data. If you have terabytes, you need something bigger than a computer to analyze, process it. Then you will need, as I tell you, a clusters. All these clusters will be deployed in the cloud, will be built upon different technologies, or the well-known cloud providers like Azure, Amazon, or Google, or your own deployment, usually using Kubernetes. But we don't center on this in this speech, and we just center on the part that you are having already deployed a cluster, and you have, let's say, to deploy something on top of it. Also, we can have data that is moving in a high velocity. This means that a lot of data is being produced in each moment. Also, a lot of social media, when there is something happening, have some peaks of activity, and it's not only the volume of the data, but the velocity in which it is produced. Sometimes the information comes in different aspects. Could be multimedia, could be unstructured data. So we have also a problem of variety. This means that the data doesn't come perfectly per format or in just one format. So here we have also a problem. And the last one is the uncertainty of the data. We have there a problem with the, let's say, the accuracy of the data. There are different kind of processed data that is not accurate enough, and you can get accurate if you have a lot of, for example, a lot of data available from one thing. For example, you can have the temperature with a very perfumed a device that is able to determine perfect it, but could be expensive, or you can have a lot of small devices and you can do processing with it. Usually, most of you are data scientists that you are used to handle the data and do the machine learning things and these kind of things. But the things we're referring here comes from something that is called data engineering. Data engineering is the task to build this kind of big data systems. Have a lot of things in common with the data scientists, but the tools are slightly different. As I tell you, everything has to be able to scale and to be able to be parallelized in order that we can handle a lot of things. And these problems usually are not cared about the data scientist. We have different tasks related here, and you saw that also the tools are slightly different. As you can see in this image, it depends on how you saw the problem. Usually the data scientists just center on what are the better parameters for the algorithms of machine learning or things, the accuracy or whatever. And usually the data engineer takes care of another things, that if you are able to handle all of this information, you are able to digest it, or what you are able to do with those kind of things. Also, the tools are different. You will see here that there are some tools that you have to have in common, but you have to handle the problems that we are not touching today of databases and deployments and these kind of things. Here you have the usual data languages that you are using, like Python or Julia. This is very common for data scientists, but as I told you before, are not the ones used by data engineers usually, because they need to be able to parallelize this. This is why we will center on Spark and in Scala languages. This is the only one that allows really seamless evolution and a seamless way of having really any kind of cluster working in parallel with all these kind of things. Around this appears a lot of things. And right now, there is a lot of things going on. We have the Internet of Things. A lot of this data is being provided inside the FIWARE ecosystem, but we have different things. Artificial intelligence is different from machine learning. Well, machine learning usually considered as a subset from artificial intelligence. We have the processing of big data. Big data could be done with machine learning or without machine learning. Today, we will see a case that joins both. And now with all the fashion about digital twins, we have augmented reality. And also we have trust on the data using usually blockchain technologies. We will center today on these two, in machine learning and also on big data, and see how we are able to handle. Well, you are not supposed to see this, but I mean, to see this slide. This is something that is showing all the ecosystem and tools that are being used right now for data, especially for big data. I have just updated because just saw that yesterday appeared the new version for 2020, and we can see a lot of tools there. You can watch it. You go to this link, you can check the image, but we can see what we are centering here today. We have different tools and frameworks for handling all these kind of things, the query of data and the data access. But as you see here, the main line here is that we have for really handling this Spark and Hadoop. These are the main frameworks that are able to handle data, not only machine learning, but other kind of soft processing in a real parallel way. We have also Flink that is also interconnected to the FIWARE framework, and there we have a lot of things there. Hadoop has been updated, we will see now, due to some technical things. So right now, the main environment that people is using is Spark. As I tell you, it is used by the biggest companies because it's the only one that is able to parallelize all the things, and is the only one that is required to use really big data. As you see here, we don't have anything like things based on Python and other languages, because these are not really for this kind of things. These are very good for data scientists, but not for data engineering. The usual architecture that we're having here is what is called land architecture. We have different things. We have one layer that is the one that is being used for real-time information. We will use this today. And also a batch layer that is the one that is using for data that you have all the data. Usually the batch layer works in a way that you get all the data, and once you have it, you process it. In the land architecture, you are processing the data as it comes. The framework for Spark comes with the both options. You can use normal Spark or streaming Spark for this kind of things. Also, there is a simplification that is the Kappa architecture. That is more or less the one we're going to use here. That is the one that is using only the, let's say, the real-time architecture. We have all this interconnected in the FIWARE architecture. We tell you, we have all the IoT and the information source. All this goes into the context broker, and here we can connect to different things. You can use the Cosmos connectors to connect it directly to the different processors, or we can use it Draco, that is the one that doing data ingestion for this kind of things. Depending on the scenario, we can put Draco or not. But you must consider this depending on the things that you can use or ingest. For example, if you want to send it to the usual storage for this kind of thing, that is the HDFS, you should use Draco. But as I tell you, we have direct connectors to Spark and Flink, and you don't need this in other scenarios. As I tell you, depends on the scenario that we are having. All the ecosystems, Hadoop have a lot of tools, but we have selected the more suitable for this kind of things. As I tell you, Flink and Spark are the more considered. Yarn is a usual, very simple orchestration, but as I tell you right now, you can use it with Kubernetes or another kind of orchestrator. So keep it is something to keep everything alive. And usually you store it in the HDFS, that is the file system for all these kind of things. Why we are using Spark instead of Hadoop? Well, Hadoop have a very limited set of functions. It's map reduce, it's basic two operations, two functional operations, the map and the reduce ones. And Spark is have a more higher variety of different things and different data. And also, every step that Hadoop is doing is sending to the disk. This means that we have a latency between different steps. Spark is using something that is called RDDs, that is resilient distributed data storage that makes the same role that the storing things here, and means that everything will be in memory. As you know, the latency of memories and this are very different, and it means that Spark is quite faster. It's better, but also it have from 1 to 2 times to orders of magnitude faster than Hadoop, because doesn't have to write everything in the disk. Usually you can use it with another environments, but we recommend you that you learn Scala. As I tell you, Scala is a functional language, very good one. It mixes all the functional language or with object-oriented programming. And also there is a distributed model that is called ACA, that is based on distributed actors, that is used by the industry, for example, inside Kafka. And this means to build a Spark with Scala. You can use it with another language, but the only one that allows you to do all the things is Scala. We really recommend you, if you are going into this kind of work, that really takes the time to learn Scala for doing all these kind of things. Well, Spark we can connect with a lot of systems, and we have different parts of it. We have the streaming, the SQL that is intended for making queries to the data, the machine learning, this is the one that we're using here, one for graph, another that is means the core of everything that is working inside the Spark. So we have these different libraries, but it goes over a common framework. This means that inside your solution, you can use the 4 libraries, or just use the Spark thing. Depends on the things that you are doing and whatever you want to do. I don't want to enter in detail, but it makes graphs of the different tasks that have to be handled, and in a very flexible way, and due to the fact that it's functional, is able to parallelize without human intervention. This means that you can dynamically add and take out machines from your cluster, and it will recalculate the way that these graphs, that means which task is going to which machine in the cluster, will be done automatically for you. Well, we have all these kind of things, but we want to use machine learning. As you know, machine learning is something that is very good for some cases, not for all of them, but for a lot of solutions that we have here. And we have a lot of different machine learning algorithms. Not all problems match the machine learning things, and we have to change different things on this. So we have different tools, and that will depend on this. Spark have all the machine learning algorithms that we are able to parallelize. This means that it takes advantages of a cluster. Some algorithms are very good, and you have inside TensorFlow, for example, but some of them cannot be parallelized. These are not inside Spark. There are different families where you have different algorithms in these kind of things, and some of them, as I tell you, can be parallelized and another not. Other subject is the use of different GPUs. This can be connected to Spark. In fact, the Spark and TensorFlow can work together to solve some kind of problems. But let's say that you have to know more or less which are the different algorithms, how your data is, and then select one for this. How we handle or we do different things with machine learning. There are mainly 2 phases. One of them is I had a subset, that is the one that I'm using for training. I will use it for building the model. When I have the build the model and make the machine learning model, I put this inside the system, and then I put everything in production. Then I can use the data, and usually I can iterate over this process in order to have my system. This means that I have 2 phases. One, use a subset of data to build the model, and other that is to deploy the model in production. In our example, we will use 2 phases. We will do doing this with Python, and we will do this with Spark Scala. In order you see that both are interworking and are used for different kind of things. We will use a very simple one that you can easily understand. Not all machine learning algorithms are really, let's say, able to understand in an easy way. But this one is very more or less easy. We have a decision tree that more or less the size is a flowchart where we are taking decisions. Even Some of them you can understand it. The ones that are being generated usually are not very easy to be understand. But since once decision tree could be not enough, our system will generate a forest of them. This means that the algorithm will just generate a family of different decision trees, and later we will mix everything in order that we design this. In our case, we will use the random forest classifier, and this means that we will select different selectors. We will make a voting between them, and this will give us the final result. Well, after this fast introduction, we will move right now to the real case. Our real case is, for example, you are going to the airport, you have a traffic jam. You know if the flight will be delayed and you are able to arrive it. Well, our system will help you and will try to predict the delays. Now, Sonsoles and Andres will introduce you to this.
Okay, thank you, Joaquin. Now we are going to present an example of how all the technologies, well, some of the technologies that Joaquin presented before, we can apply using the FIWARE ecosystem. In this case, we are going to present you a little example of an application of flight predictions. So using all of the FIWARE architecture and some data coming from a web application. In this case, you can see in this slide a little overview of the architecture that we are going to use. In this case, we are going to use components like Spark, in this case in cluster mode. We are also using FIWARE Cosmos as a connector for receiving the NGSI notifications coming from the Orion context broker. In this case, we use the context broker for receiving all of the information that we generate from the web applications, and also all of this information will be stored using MongoDB through FIWARE Draco that will be subscribed to Orion. This is a little overview of the architecture. We are going to talk about it more in detail in the next slides. In this case, well, here we have a little overview of the 3 key components that we present in the previous architecture. In this case, we have the Orion context broker that allow us to create and receive NGSI v2 notifications from the web applications. All of this information is in NGSI v2 format, but we can also use NGSI LD for managing all of the information. We are also using Cosmos as a connector for, in this case, Spark, but we can also use this generic enabler with Apache Flink. But in our example specific, we use Spark for the training, the model, and also for the streaming context that we receive from the web application. Finally, we use FIWARE Draco to storage all the historic context coming from the context broker. Using, in this case, Draco, we can store the response about the prediction that we have in Spark, in this case. Well, now I think Sonsoles will present you all the details in the of the code. In this case, I think.
Yeah. Can you hear me? Can you hear me? Yeah. Okay. So we have the code for the whole use case available in this GitHub repository in case you want to take a look at it. Andres, if you can maybe paste it in the chat so people can easily access it. So the example that we're presenting, the complete use case used in the whole architecture, FIWARE architecture, and Spark is for flight prediction, as Joaquin said earlier, and others as well. So the first step to provide a flight prediction service would be to obviously gather data from flights that took place in the past, so we can use those data to predict what's the delay of the flights that are going to be taken off in the future. So we gathered this data set from the Bureau of Transportation Statistics of the US, which contains almost all the flights that happened in the US with Orion in the US in 2015, which is like around 500,000 flights. And we use this information to train a predictive model that allows us to predict any delay for any flight in the future. So some of the relevant fields that this data set has have to do with obviously with the dates of the flight. Maybe flights that happen in Christmas are usually more delayed than the rest of them, for instance. The airline of the flight also is an important, might be an important predictor of the delay. The flight number, the airport of origin, obviously very important to predict. Maybe bigger airports are more usually more tend to delay a flight more. The airport of destination, the initial departure delay, and the arrival delay, which is actually what we want to predict. At the bottom of the slide, you can see an example of a raw image in this data set. And if you want to take a look at it, you can download it from the link from the slides that you will have available at the end of the webinar. So now that we have our data, we have to train this predictive model. We chose the random forest classifier algorithm. There's a lot of algorithms that Spark machine learning, Spark ML has available, both classification and regression, depending on your use case. In the slide, you can see the link to the Spark documentation in case you want to check them out. And what we're going to do with this algorithm is use the data from the data set and use this random forest classifier algorithm to create this predictive model. If we take a look at the code here, we can see that we are using Python because as what we wanted to show that the Spark can be used from different programming languages. In this case, we're doing the training with Python because, as Joaquin said earlier, many data scientists don't know Scala. So you can see we can do the training or the part that is kind of offline with Python, for instance, and then export the train model into a common format that can be imported from Spark Scala, so it can be used in production ready systems. So what we do in this code is we extract the features from the data set, and we just convert each column, each field in the data set to its right type. And first we need to, like I'm sure you know, we have to do some preparation steps for the data so they're ready to be entered into the random forest classifier algorithm. For instance, we convert string fields into different categories, and we have to normalize the data. And in this case, what we're doing is, instead of predicting a specific numerical output, like the number of minutes that the flight is going to be predicted, it's going to be delayed, we are dividing this delay into 3 categories: on time, slightly late, or very late. This is what we're using the random forest classifier. If we wanted to actually predict the number, like any number of minutes that it's going to be late, we should use the random forest regression algorithm. So these are all the preparation steps for the data. We combine the numeric fields with the categorical fields, and down here, we finally use the random forest classifier. We say which are the in which variables we have the features that we want to use for the prediction of the delay, and which one would be the output of the variable we want to predict, and which are the names of the possible outputs. And we also can tune some of the hyperparameters of the algorithm that will probably affect our output. We then fit this model to the data that we have, and then we can save this model into a common format that, as I said earlier, we can import from the prediction program, because this is a training program. So we can use it in this case in even another programming language that is not Python. Here at the bottom of the program, we see how we evaluate how well our classifier performs, and obviously, in the training program, the data scientists can do any functions, any tests that they want. But what we're interested in as data engineers would be just this output of the trained model. So going back to the slides, we just did our training and we got the model. So now we're going to see how we can use this model to perform predictions. So now what we are doing with this model is to get new requests for new flights that our model has not seen before, flights that haven't happened yet, haven't taken place. So we're missing the arrival delay feature, because that's the one we want to predict. So now, thanks to Spark streaming, we're going to receive in real time. Whenever one user wants to make a prediction for a specific flight, we're going to receive it in our trained predictive model, and we're going to compute the predicted delay. So in order to, as I showed earlier in the architecture, I'm going to show it again. We're going to deploy our Spark Scala prediction program in this Spark cluster, and we're going to have the user enter the information for the flight in a web interface that we'll see. This will go to Orion, and Orion will notify Cosmos, which is where the program will be running. That's in the Spark cluster. And thanks to this, the Cosmos connector, we will be able to use Spark streaming to receive this notification that there's a new request for prediction in the context broker, and link it to our prediction program. If we take a look at the prediction program, we see that we're not using Python anymore. This is Scala. And what we do is we import the model that we trained earlier. As I said, this even though this was in Python, exporting it to this common format allows us to use it in Scala. And we are going to use the Orion receiver, which is the Spark connector from the Cosmos generic enabler, to listen to the stream of events coming from the context broker. Sorry. So we're going to again extract the different attributes that our request for prediction has: the origin of the flight, the departure delay, the destination, the date, the carrier, etc. And we're going to make a prediction request object, and we're going to use that as the input to our predictive model. Here, after the data transformation that we did also in the training part, we're going to get the prediction, and we're going to create a prediction response object. This number just means that we're only getting the part of the data that belongs to the prediction volume. We're not using the rest of the input features, because we already have them, so we are not sending them back again. And the rest of the other two fields that we're sending back deal with the client ID and prediction ID so we know to which user we need to show this result. Otherwise, we would just lose who requested this prediction. So the resulting stream of of prediction response objects, we send them to Orion using the Orion sync. So anybody that is subscribed, any component that is subscribed to this entity where we store the prediction results can receive this, can be notified that there's a new result for a prediction. Okay, so this is a screenshot of the web interface. As you can see, the user would need to fill in this form specifying the information of the flight that he or she wants to predict the delay for. And once he or she clicks submit, they will get the predicted delay. As I said, it's not a fixed value, but it's just like a category. It can be on times like late or very late. So the web server is also built with Python using Flask, and it's connected to the front end part is connected to the back end through socket.io. So this means that when the prediction result is available through the socket.io, we would get it immediately on the web interface. Normally, since the prediction can take a bit longer than a normal HTTP request, it's not a good idea to do it just as a regular AJAX or synchronous request to the web server, because it could take a bit longer. So we will keep the server hanging. So in this case, the use of socket.io is just because we need the server to be able to notify the web client whenever the response of the result of our prediction is ready. So now Andres is going to present the different entities that we are going to use for the prediction and the result of the prediction. And hopefully with this and the next slide, which explains again the whole process, we'll get a more clear picture of what's going on behind the scenes.
Okay, thank you, Sonsoles. Well, in this case, we are going to center all of the presentation in the context broker. So in the context broker, we need to have created two entities, one for the request and one for the response, and also the subscriptions to that entities for receive and they receive all the information from the different point of the components that we have. In this case, the request entity presents all of the information that coming from the web application. In this case, when you fill the form in the web application, you send all of this information in NGSIB2 format to the context broker. In the context broker, we have that entity, and with that information, we are going to update the attributes. When the attributes are updated, the notification is generated and sent to a Spark through the port that you can see in the slide. The other entity is the response entity. The response entity contains the output information from a Spark, in this case, from our machine learning model. So when some request is made to a Spark using the machine learning model that we trained before, this machine learning model sends an output with that information. In this case is the prediction ID, the socket ID, because as Sonsoles told before, we are using WebSockets in our application. We need the socket ID. And finally, the prediction value, that is a value between 0, 1, or 3, 0, 2, or 3, if I am fine. So this information, this output is going to be notified to the different components that we subscribed before. In this case, the web application and Draco. The web application will present the delay that we have with the input parameters, and Draco will store the historic context in the MongoDB. So in the next slide, we can see the whole interaction using every component in the architecture. First, the user make a request using the web applications. So send the information to the context broker. So the user fill the form and click and submit, and this information coming from the web application is sent to the context broker. The context broker notify directly to the Spark cluster using the Cosmos connector. So Spark, using the machine learning model that we trained before, sends an output to the context broker again. So this information updates the response entity and sends a notification to Draco for storing this this entity in MongoDB. Once we receive the same response prediction value, the context broker notifies also the web application, and the web application presents the results to the user. So this is a complete interaction in two ways of how we can use the web application and the whole process of prediction using the whole component of the architecture. So in the next slide, we are going to present you a little demonstration, a little video with the whole process from cloning to the repository, deploying the containers, and making the predictions. In this case, we're starting from scratch, cloning the repository. This takes just a little of time. Okay, once we have the repository clone in our directory, we are going to execute the script for deploying the whole scenario. The whole scenario is built on Docker containers, so we have the whole process as microservices. So in this case, the process starts downloading the data because the data is not in the repository, it's in an external repository. So first, we are receiving the whole data in our directory, and then we are going to train the algorithm using different containers and using the program that Sonsoles showed you before. In this case, as you can see, in the models folder, we don't have any machine learning model stored. So once the training stage is done, we have the whole information in that folder, in the models folder. Once we have the model stored in our local repository, the training containers will stop, and then we are see that the prediction containers starts. In this case, we are going to see the output of how the containers are setting up. In this case, we have the web server and the Spark containers. We have also some additional containers that run some scripts for create the entity and subscriptions in Orion. And as you can see, we can see the web container, the Spark. Okay, the Spark deployment takes a little longer than other containers because he is deploying the job and also creating the streaming context for receiving the whole information that is coming from the web application. So in this case, this process takes a little of time. So I present it, as you can see, because in some point, Spark show you how the program is ready to start. So in this case, we have to wait just a little bit more. Okay, and in this point, if I am right, yes, we can see the output from Spark. We can see the data frame structure and also what information we are receiving. So we have here the web application, and in this tab, the Draco web interface. So well, in this case, we need to wait a little more time for Draco, and here we have Draco with the whole processors running in this case for storing all the information in MongoDB. Okay, if we click in submit in the web application, we can see how this information is passing to Orion and then to Spark. So in this case, you can see in the output, we have the prediction here. We have the prediction, and you can see in the web application that we have the prediction. In this case is from 0 to 15 minutes of delay from that flight. So if we check the data provenance in Draco, we can see that the same information was sent to this component, and after that is going to be stored in MongoDB. The same thing, the response notification that we receive from that request. Okay, if we perform another query or another query for this program, we can see that if we change the departure delay, we have more delay in the flight according to the historic record that was used for training our model. So if we check again the data provenance, we can see that the information is updated also in Draco and after that in MongoDB. So this is all from the demonstration. As you can see, using the repository that we provide you in this webinar, you can deploy the whole scenario, and the only thing that you need to have previously studied is Docker, Docker Compose, and Python. As you can see, it's very easy to deploy. Then you can go deeper in the code for trying to understand a little more about how the whole process is developed. But you can use this for start testing or start coding some things with machine learning and FIWARE. Finally, I want to provide some extra slides. If you want to know more about big data and how you can use Cosmos and Spark and Flink, you can see our previous webinar that we present months before. And in this case, we present a supermarket example, more or less with the same dynamic that this presentation, using the more or less the same generic enablers, but a different data set and a different program for training and for the prediction job.
Yes, this way you can see how the same architecture is easily adapted to different use cases, different contexts with the same generic FIWARE architecture. We also invite you to check out the tutorials that we have on Cosmos or Draco, step-by-step tutorials that will show you how to link these generic enablers with the rest of the FIWARE components.
Okay, I think this is all the presentation. Thank you for watching, and if you have any question, please let us know.